Observe these processes carefully. Place some dried fruits and vegetables in water. They slowly swell up and return to their original form. When a raw mango is placed in concentrated salt solution, it loses water and shrivels into a pickle. Similarly, if we place wilted flowers in fresh water, they are revived. All these processes have one thing in common. There was a flow of water molecules either to or from the substance. Secondly, all the substances were bound by membranes. This phenomenon is called osmosis. Small solvent molecules like water can pass through the holes of these membranes, but bigger molecules like the solute are unable to pass through them. Such membranes, which are selectively permeable to only certain molecules, are known as semi-permeable membranes or SPM. These membranes can be of natural origin or synthetic origin. Vegetable membranes, which are found just under the outer skin, like in the onion, membranes found under the shell of an egg, a pig's bladder, or parchment are examples of natural membranes, while cellophane is an example of synthetic membrane. Osmosis can be defined as the spontaneous flow of solvent through a semi-permeable membrane from a pure solvent to a solution, or from a dilute solution to a concentrated solution. It is important to note that osmosis drives solvent molecules through a semi-permeable membrane from low solute concentrations to high solute concentrations. Osmosis ends when the solute concentration becomes equal on either side of the membrane and equilibrium is attained. The flow of solvent molecules from low concentration to high concentration can be stopped by applying some extra pressure on the high concentration side. The minimum pressure required to do so is known as the osmotic pressure of the solution. Thus, osmotic pressure pi of a solution is defined as the excess pressure that must be applied to a solution to prevent osmosis from taking place. Osmotic pressure, like other colligative properties, does not depend on the identity of the solute, but on its concentration. It has been found experimentally that osmotic pressure pi for dilute solutions is proportional to molarity C of the solution at a given temperature T. Thus, pi is equal to C multiplied by R multiplied by T, where R is the gas constant. If the solution contains N2 moles of solute in volume V, then C is equal to N2 divided by V. Therefore, pi is equal to N2 multiplied by R multiplied by T divided by V. If W2 grams of solute of molar mass M2 is present in the solution, then N2 is equal to W2 divided by M2. Substituting this value of N2 in the earlier equation, we get pi equal to W2 multiplied by R multiplied by T divided by M2 multiplied by V. Rearranging the equation for M2, we get M2 is equal to W2 multiplied by R multiplied by T divided by pi multiplied by V. This method of measurement of osmotic pressure is widely used to determine the molar masses of polymers and macromolecules, especially biomolecules, as they are generally unstable at higher temperatures and decompose before their boiling point is reached. This method has the advantage over other methods as osmotic pressure is measured around room temperature and the molarity of the solution is used instead of its molality. Let us now solve a numerical problem based on osmotic pressure. 1 liter of an aqueous solution of a protein contains 10 grams of the protein. The osmotic pressure of such a solution at 300 Kelvin is found to be 2 multiplied by 10 to the power minus 3 atmosphere. Calculate the molar mass of the protein. The given variables are W2 is equal to 10 grams, V is equal to 1 liter, T is equal to 300 Kelvin and pi is equal to 2 multiplied by 10 to the power minus 3 atmosphere. M2 needs to be calculated. Also, R is equal to 0.082 liter atmosphere per Kelvin per mole. Substituting these values in the equation, M2 is equal to W2 multiplied by R multiplied by T divided by pi multiplied by V. And solving, we get M2 is equal to 1,23,000 grams per mole. In other words, the molar mass of the protein is 1,23,000 grams per mole. Let us consider two solutions with concentrations C1 and C2 at temperature T. Then osmotic pressure for the first solution, pi 1 is equal to C1 multiplied by R multiplied by T. While osmotic pressure for the second solution, pi 2 is equal to C2 multiplied by R multiplied by T. Now, if the solutions have the same concentrations, that is, if C1 is equal to C2, then pi 1 becomes equal to pi 2. It means that equimolar solutions at the same temperature have the same osmotic pressure. Such solutions with the same osmotic pressure at a given temperature are called isotonic solutions. When such solutions are separated by a semi-permeable membrane, no osmosis occurs between them. It is because of this reason that in an intravenous injection of 0.9% mass by volume sodium chloride solution, called normal saline solution, is used, since it is isotonic with the fluid inside the red blood cells. A pure sodium chloride solution with the concentration more than 0.9% mass by volume is called a hypertonic solution. And red blood cells shrink when placed in this solution. On the other hand, a pure sodium chloride solution with a concentration less than 0.9% mass by volume is called a hypertonic solution. And red blood cells swell up and may even burst when placed in this solution. It is important to note that a high intake of salt in the diet can lead to a higher concentration of fluids in the body tissues because of osmosis. This will result in swelling and puffiness of body parts, which is known as edema. It is of interest to mention that if a pressure greater than osmotic pressure is applied on a solution, then the solvent will flow from the solution to the pure solvent through the semi-permeable membrane. This process is known as reverse osmosis and is often used for the desalination of seawater for getting fresh drinking water. Desalination of seawater is carried out using a cellulose acetate semi-permeable membrane placed over a suitable support. This cellulose acetate membrane allows the passage of only water molecules through it and is impermeable to the salts and other impurities present in seawater, thus making it fit for drinking.